Hello APC Mechanics students in Unit 5 Rotation Class 4 5.1 Moment of Inertia. Now Section 1 Moment of Inertia Particle-like Object. As we are developing rotational mechanics formalism, the applied force has been promoted to torque. Now we need to promote inertia. By inertia we refer to the mass in order to introduce different missing laws. Inertia or mass in rotational dynamics is not only about the quantity itself, but also related to the mass distribution about the axis of rotation. Consider an axis of rotation delta and an object of mass m1 at a distance x1 from the axis of rotation. So this is basically the axis of rotation, delta, and we have a mass m1 at a distance x1 from this axis of rotation. So the object is a particle, like the dimensions of the objects are negligible, so the object is very small in size. We define the moment of inertia, the resistance to motion, to be given by I, which is m1 x1 square, where m1 is the mass of the, I is the moment of inertia. The moment of inertia has unit which is kilogram meter square. m1 is the mass of the object, and x1 is the distance from the center of mass of the object to the axis of rotation. Now, what I'm trying to say here is that the analogy of mass in rotation would be the moment of inertia, because it's not only about the mass itself, it's about the distribution of mass along the axis of rotation. The moment of inertia I is an additive quantity similar to mass, which means if more particles like objects are invited to rotate around in our system around delta, like m2, m3, m4, then the total mass or the total inertia for rotation would be given by the summation of mi xi square, and that would be m1 x1 square plus m2 x2 square plus m3 x3 square plus m4 x4 square. Depend on the number of objects that are rotating around the axis of rotation delta, and notice that here I'm summing over the distance for the respective mass, which is I1 plus I2 plus I3 plus I4. Now, to determine the moment of inertia for an extended object like this one, which consists of infinite number of infinitesimal particles, first the axis of rotation should be specified. So this is the axis of rotation. In this case, I'm considering it to be at the center of the rod. After that, we need to divide the object into differential masses, dm1, dm2, dm3, dm4, up to infinity, and we have done this trick in order to determine the position of the center of mass for an extended object as well. The origin itself would be taken to be the axis of rotation. So here, pay attention. So first we specify the axis of rotation, and based on that, we will specify the origin. Okay. Now, then the moment of inertia of the given extended object with respect to the axis of rotation is given by summation from I up till infinity to dmi xi square. If you refer to the previous formula, it was given by I summation of mi xi square. So here the masses are differential masses, so I'll add d, because we're dividing it from a given value up till infinity. As we divide the given object into more and more infinite differential masses and the limit of producing the full extended object, the summation operator will be promoted to an integral. And we know that in this case, the moment of inertia for the extended object is given by the integral from the initial position to the final position into x squared dm. Now here, notice two things. We have two mixed variables, x on one hand and the mass on the other hand. So in order to integrate this fully, the integral should be unified in terms either the variable x or the variable m, where the boundaries of the integral are set based on our origin. So these might be positive and might be negative. So in this case, if this is L and this is our origin, so the integral would be from minus L over 2 into L over 2. The integral is a composite of variables, both position and mass. Both variables can be unified using density mass distribution. What I'm trying to say here is that the mass can be unified into position by recall that lambda, which is the linear mass density, is given by dm divided by dx. that would be given function of x, so dm would be lambda dx, and that would be replaced in the integral itself. Remarks: this method works for both mass distribution, uniform and non-uniform. So in order to find the moment of inertia so first of all, here we're talking about extended object. The extended object might be of uniform mass, so uniform mass, or even non-uniform mass. Both, this method works for both types of masses. Always choose the origin to be the axis of rotation itself, and this is very important. So first we choose the axis of rotation, we specify it, and the origin would be chosen at the axis of rotation. Now section 2, moment of inertia for an extended object. Now here we have certain type of objects that are specific. We would like to introduce their moment of inertia. Let's start by a hoop, which is a ring. A hoop of mass m and radius r, where the axis of rotation passes through the center of the hoop. Now the axis of rotation passes through the center of the hoop. The mass is contained only in the rim. R is the radius of the hoop. Then its moment of inertia is given by mr square, which is similar to the object without dimensions rotating around delta. Now for a sphere of mass m and radius r, so it has a radius r. The axis of rotation passing through the center is 2 over 5 mr square. You can ask for yourself, so what about if the axis of rotation now is tangent to the sphere, or the sphere is rotating around an axis of rotation passes along its rim? Then in this case the moment of inertia is greater, which is given by 2 over 3 mr square. Why this happens? Because as the axis of rotations become far away from the mass distribution or the center of mass, this means that the moment of inertia would increase. Now if you have a rod of mass m and length L, where the axis of rotation passes through the center of the rod, in this case the moment of inertia is given by 1 over 12 ml square. Now what about shifting the axis of rotation such that it passes through the edge of the rod, and it's given by, so in this case the moment of inertia would increase because the center of mass is now at a distance greater than compared to this one. Then the moment of inertia would increase, and it's given by 1 over 3 ml square. So basically the moment of inertia depends on two factors. Depends on the mass itself and the mass distribution around the axis of rotation. And you can ask yourself, how can are these two related to each other? So you can think about, how does 2 over 5 is linked to 2 over 3, or even 1 over 12 is linked to 1 over 3, and that opens the new door for the parallel axis theorem. Consider an object of uniform mass distribution and of mass m that can rotate about an axis delta passing through its center of mass. Hence the resistance of motion, or the moment of inertia of the object around delta, is given by ICM. What does ICM represent? ICM represents the moment of inertia of the rod about an axis delta passing through its center of mass. Now what we're gonna do, the axis of rotation will be shifted by distance d from the location of the center of mass. So we have shifted the axis of rotation to a new one that is a distance d from the center of mass. How come? Now the object rotates about a new axis of rotation delta prime that is distance d from delta. In this case the moment of inertia of the system changes from ICM to a new moment of inertia given by I, because we said previously that the moment of inertia depends on two factors. Depends on the mass distribution and depends on the... So basically, yes, we can say about the mass distribution, about the axis of rotation. Which means that along this axis, that would be I, along this axis would be ICM, and how these two are interconnected we will see, because the moment of inertia is not only about the mass which remained unchanged, but rather the mass and its distribution around the axis of rotation. Both I and ICM can be related very beautiful theorem known as the parallel axis theorem, which is given by the new moment of inertia is given by ICM plus this term, which compensates for the shifting the axis of rotation by distance d, and m would be the mass of the rod, where I is the moment of inertia around delta prime, ICM is the moment of inertia around the center of mass, and m is the mass of the object, and d is the distance between delta and delta prime. So remember that the center of mass plus this factor would give us the new moment of inertia. Recall that always and forever the unit of I is given by kilogram meter square, kilogram meter square, kilogram meter square. And now we can start solving the exercises for the rest of the video. Exercise 1, a 5 kilogram sphere connected to a 10 kilogram sphere by a rigid body of negligible mass as shown above. The sphere rod combination can be pivoted about an axis that is perpendicular to the plane of the page and that passes through one of the 5 letters. So we can place either the axis of rotation here, or here, or here, or here, or here, and through which point should the axis pass for the moment of inertia for the sphere rod combination about the axis to be greatest. Now, the greatest one would be such that the axis of rotation passes through E, because the greatest mass is given by 10, and that would be the largest from E, making E to be the correct answer. Now, a solid disk of mass m and radius r is freely rotating horizontally in a counterclockwise direction with an angular speed omega about a vertical axis through its center with negligible friction. The rotational inertia of the disk is given by mr square over 2. So for one disk, it's given by mr square over 2. A second identical disk is at rest and suspended above the first disk with the centers of the two disks aligned as shown in the figure above. There is no contact between the disks. The second disk is dropped onto the first disk, and after a short time they rotate counterclockwise with the same angular speed omega f. So this has been dropped and now they are one system. Then the new moment of inertia, remember that the moment of inertia is an additive quantity. Now it's given by mr square over 2 plus mr square over 2, which is mr square, and that would be representing the moment of inertia of the system of the two disks with respect to an axis of rotation passing through its center. The two disks are now shifted so that the axis of rotation goes through a point on the edge of the disks. The rotational inertia of the two disk system is now this axis of rotation has been shifted here. Now the new moment of inertia with respect to the old moment of inertia can be related to each other via the parallel axis theorem, which is I is ICM plus md square, where d represents the distance shifted from I to ICM or ICM to I, which is basically the radius. So that would be mr square plus mr square, which is given by 2 mr square, making A to be the correct answer. Now, the uniform thin rod shown above has a mass m and length L. The moment of inertia of the rod about an axis through its center and perpendicular to the rod is given by 1 over 12 ml square. So if the axis of rotation passes here, the moment of inertia of the rod would be given by 1 over 12 ml square. Now, what is the moment of inertia of the rod about an axis perpendicular to the rod and passing through the point P? So we have shifted the axis of rotation from the center to a point P, which is a certain distance away from the center of mass. If all of this is L, then that would be L over 2 and that would be L over 2. And if this is L over 4, which means this is L over 4, then the new moment of inertia is related to the old moment of inertia plus md square according to the parallel axis theorem. The old moment of inertia is given by 1 over 12 ml square plus m. The distance d is given by L over 4, and that would be to the power of 2, which means 1 over 12 ml square plus 1 over 16 ml square. Plugging that on the calculator, we're gonna get a factor of 7 over 48 ml square, making E to be the correct answer. Now, a rod with a non-uniform mass density given by lambda is ax square, where a is 5, is aligned on the x-axis with one end at the origin and the other end at x is equal to 2 meters. Now, YA has the following unit. The linear mass density is given by kilogram per meter, and in order for A to agree dimensionally, then A would be given by lambda divided by x square, which is kilogram per meter square, which means kilogram per meter cube. So you should always be able to interpret the units perfectly. Is aligned on the x-axis with one end at the origin and the other end at x is equal to 2 meters. So basically this is 2 meters. And notice that here the shading means that as we go away from the origin, the mass becomes more dense, and this is anticipated because it's proportional to position to the power 2. The rotational inertia of the rod about the origin is most nearly, so we need to determine the rotational inertia. Now ask yourself, is this a discrete system or an extended object? It's an extended object, so we need to determine the moment of inertia via integration, which is given by the formula x initial 2x final into x squared dm. Now here, before I set the initial and the final position with respect to our origin, we need to unify the variables. We have x and dm. Now dm can be simply changed to x by saying that lambda is dm divided by dx, which means that dm is lambda dx, and lambda in this case can be unified back again to x, which is ax squared dx. So that would be the integral from xi to xf into x squared ax squared dx. Now a is a constant, can be dragged out, and that would be the integral of x power 4 dx. Now our initial position would be 0, our final position would be 2. We always, in such type of integrals, this is not a line integral, this is a scalar integral, which means we should integrate from low to high. It's path independent. A is 5, then let me change this to be 5. So that would be 5 into x power 5 divided by 5. From 0 to 2, that would cancel. We can ignore the 0. Then that would be 2 to the power 5, which is basically 32. And remember that the unit of I is kilogram meter square, and making the correct answer to be C. Now, the rotational inertia of a slim rod of mass m and length L about a perpendicular axis through its center of mass is given by 1/12 ml square. What is the rotational inertia of the rod about a perpendicular axis through a point on the rod at a distance L/3 from the center of mass of the rod? And this can be determined via the parallel axis theorem. Old moment of inertia plus the new term that compensate for the change, which is mL/3 to the power 2. That would be mL square over 12 plus mL square over 9, and that would be 1/12 plus 1/9 mL square. And plugging this fraction on the calculator, we would have 7/36, making B to be the correct answer. And finally, the following exercise and an exit ticket for today's video. The rotational inertia of a sphere of mass capital M and radius r about a diameter, it's 2/5 mr squared. The rotational inertia about an axis tangent to the sphere is given by what? So that would be the old moment of inertia. We need to add a term that compensate for the change, which is r square, basically the distance d is r, because initially the axis of rotation was passing through the center of the sphere. Now it's tangent to the sphere, so we will add only this distance r. Now that would be 2/5 plus 1 multiplied by mr square, making it B to be the correct answer, because 2/5 plus 5/5, that would be 7/5 mr square. And that's it for me in this video, guys. See you soon in a new one.